Hello, Royals. Let's look at lesson 4.4 on related rates. Just want to go through example 2, maybe show the construction of the diagram, illustrate or simulate the situation for you, and make sure that we have the correct language here. In example 2, we have a 10-meter ladder is leaning against a wall. There it is, 10 meters. Let's assume the wall's vertical. And it begins to fall. The foot of the ladder slides away from the top. So what's going to happen here? Do I have a smaller ladder? Let's try this. Here's the ladder. And as its foot slides away, its base will fall. Okay. Now this is not a one-to-one relationship. It's not a the rate of change of the base of the ladder from the base of the wall is not the same as the rate of change of the top of the ladder from the top of the wall. You might be able to predict that during these first changes. What I'm trying to illustrate here is that the base of the ladder is moving away quite quickly and the height is not moving much at all. Down here, a small change in the height will cause, a larger change in the height will cause a smaller change in the base. There's a trigonometric relationship here that we'll investigate in Unit 5 when we look at trig derivatives. So we have different rates that are related to each other. It's a really good idea to organize what those rates are in the question and what we're asked to do. The question says the foot of the ladder slides away from the wall at 0.5 meters per second. So I'm probably going to want to label this rate here. And then I'm asked to determine the rate at which the top of the ladder is falling. And then I'm given an instant, either a time or a distance, a value of another unknown here, when the foot of the ladder is 6 meters from the wall. Now, I'm not going to put that 6 meters on here because that's related to an instant. I can't use that 6 meters to figure out what the height is, and then like knowing how high the ladder is right there right now doesn't tell me anything about the rate of change. I need to relate my rates before I substitute in given information. This is the same as if I'm looking at a quadratic curve, y equals x squared, and I want to know the slope of that curve when x is 4, I don't substitute in 4 first. I don't actually even need to know the height of that function to figure out the rate of change. Okay. So what is it that I'm given and what is it that I'm asked to find? Instead of starting by relating my rates, I like to relate my unknowns here. I like to organize my unknowns. I'll call this distance B, and I'll call this distance A here. And maybe even before declaring my variables, I can record the information that I'm given. I really like the approach of using given, find, when. So here's your quantities or your rates. Find whatever unknown rate or quantity you're looking for, and then here's your instant. So in this question, we are given how quickly the base of the ladder is moving away from the wall. I would call that the rate of change of the base with respect to time. It is a rate of change of a horizontal distance with respect to a measurement of time in seconds. And I'm given that that is positive 0.5 meters per second. I'm asked to find the rate at which the top of the ladder is falling. I've decided, or I will decide, to call that distance the altitude or the elevation of the top of the ladder above the ground in meters, A. So I'm asked to find how quickly the value of that variable is changing with respect to time. And I'm asked to do that when. Am I told the time in this case? No, because I'm not told the initial conditions. I don't need to know where the base started in this question. That seems like it might be a useful piece of information. That would be necessary if I was asked to find dA by dt when t equals 4 or something like that, 4 seconds later. But I'm not. The instant that I'm given here is more of a snapshot of the situation. I'm asked to find dA by dt when the foot of the ladder is 6 meters from the wall. So this is where I'll record my instant. But I'm not going to use that value first. I'm usually don't use that value until the very end. Okay. All right. the two approaches that I advertised, I think I'm really just going to stress the first one in the video because I think it's, well, we'll see. I believe it is the most efficient approach. In order to relate your rates, I suggest that you relate your quantities first. So I'm going to relate, after I declare my variables, I'm going to relate my quantities. Now, notice the variables that I have here, A and B, that have to be declared. But since I'm differentiating with respect to time, I also need to declare that variable and its units. So let's let A, B, and T represent the altitude of the top of the ladder, the distance from the wall to the base of the ladder, and time. In A is in meters, M is in meters, T is in seconds. That way I don't have to write 3 let statements. Just be careful if you're going to try to do 1 let statement and make sure you're keeping everything in order. You can't randomize the order of your variables and expect your units and expect your reader to figure that out. Okay, so here's my relationship between my quantities. I see a Pythagorean relationship. I see that a squared plus b squared is going to equal 10 squared. And if I'm trying to find dA by dt, I do not need to isolate a right now. You could do that. In the lesson, I believe I used implicit differentiation instead. And that's actually the approach that I'm going to stick with here. The desire to isolate a usually comes from students just wanting to have a function for a, and then they want to find dA by dt, or like a prime of something. But if we're not using Lagrange notation, we won't feel that pressure to have this, if you want to call this, excuse me, if you want to call this the dependent variable, maybe we should have a chat about that. It's not really more dependent than any other. Okay, so I'm going to say let's just differentiate implicitly. I'll take the derivative with respect to time of both sides. Then I just have a couple of chain rules here. I'll take the derivative of a squared with respect to a, multiplied by the derivative of a with respect to t. I'll take the derivative of b squared with respect to b, multiplied by the derivative of b with respect to t. And I'll take the derivative of a constant. In the printed lesson, I discussed how if you used L here for the length of the ladder, you would have 2L times dL by dt. And then ask yourself, well, how quickly is the length of the ladder changing? And simulating this experience will show you that the length of the ladder is not variable. Sorry. Students often get confused about labeling, declaring unknowns versus labeling variables. The length is not variable or unknown in this case. So its derivative is known. Okay. Now you can simplify this expression a little bit, maybe by dividing both sides by 2. Just go up here and say that a dA by dt plus b dB by dt is going to equal 0. And if you're interested, you could rearrange and isolate and find an interesting relationship between these rates and their lengths, very much like the first rectangle question. The rate of change is going to depend on the other rate and the specific distances. But I'm still going to argue against isolation here and just say that we should be able to substitute in our given information and take a look at what's missing. So let's take inventory. This is what I want to find. Okay. This is known. I've got that. And B is known. So now I recognize that A is needed. And I alluded to the fact that we could have calculated A right from the start, but I don't feel like that's a great way to begin the question. As you'll find in example 3, for example, with the street light, that sometimes there are unknowns that you do not need in the question. You're not expected to know You're not expected to know what you need to know when you start the question. Wait until you get to the stage where you have your wanted quantity showing up in your expression, and then you can decide what is required. And if you don't like what is required, you could try to take a different approach through the question. So this is when and where I feel most comfortable saying when b is equal to 6, and this is when and where I'll draw the sketch with the base being 6 meters away. And I'll just show my work here and say that a is going to be just the positive root of 10 squared minus 6 squared. That's going to be 8. Okay. Now Leibniz notation is a little bit awkward for saying when you're substituting, saying like dA by dt when a is this and b is this and dB by dt is this. But if you've organized your information for your reader, if you've presented what was given up here, sorry, you can't see it anymore, then your reader should be able to follow when you say, I am going to substitute all knowns. And I'll get, from this line right here, A is 8. Did we look at units? Let's look at units in the example here. dA by dt is what I want to find. That's unknown. B is known to be 6. And dB by dt is, let's just go to a fraction here, 1/2 of a meter per second. Equals 0. Same argument about the units here as before. You don't need to substitute them in, but it's kind of nice to see how they work out. dA by dt then is going to be the opposite of 6 meters multiplied by 1/2 of a meter per second. Don't know why those are outside of the brackets. Divided by 8 meters. Let's say that this 6 meters and those 8 meters, that those units eliminate. And I'm left with dA by dt in meters per second, which is what I wanted. I take half of 6, I get -3/8. And then it's up to me to interpret the sign of this rate here. This means that, as I expect, if I simulate the situation, that the top of the ladder is falling when the base of the ladder is increasing in distance. Sorry. If we were to, say, try to push this ladder, if we're, I don't know, like raising a barn or something, if we're pushing this ladder up, then when dB by dt is negative, dA by dt will be positive. I need to figure out a way to get my hand out of the way there. Okay, so I will interpret this and say at that instant, apologies, the top of the ladder is falling at a rate of 3/8 of a meter per second. Okay, don't repeat the negative in your conclusion. The negative has been translated to mean that it's falling here. And be careful about, like, just mention something about at that instant. You don't need to say when, repeat the entire question, when the base of the ladder is 6 meters away, but I want you to recognize that you've discovered right here that this rate of change is not constant. It changes based on how fast the base is moving away and what these distances are as well. Okay.